Okay, here's another problem. Is this block moving? I have the plane is 33 degrees. I've got 2 kips load. I'm pushing upward with 0.7 kips. The static coefficient of friction is 0.2. The kinetic coefficient of friction is 0.11. And then the other part of this problem is to draw the final free body diagram. So take a look at this problem. I'll give you a hint on how to, you know something about friction now, so you should be able to do this, but I'll give you a hint. First, find the forces under equilibrium. In other words, first assume it's not moving and find out what the forces are on it. Start there. So pause the video and do this one. Okay, so find the forces needed for equilibrium. Well, that's simple because we've been doing that. There's my free body diagram. Again, this angle is going to be 90 minus my theta, and another 90 minus the 33 degrees. So that's 57 degrees. And again, I'm making a cut. I've got that for me, a cut through this frictional surface, which means that I have an N and an F there. And I'm going to take the sum of the forces equaling 0 to get my N and F. So when I do that, well, by now you should be able to get that I'm taking forces in the y direction, because remember we're doing our coordinate system like that. I have that going in the y direction. I have the component of that going in the y direction. So I've got n minus 2 sine 57 degrees, sine of the angle, again because it's y. And I get n equals 1.68 kips. I then use that, or then I take the sum of the forces in the x direction, equaling 0. So I've got that in the x direction, I've got that in the x direction, and then I got the component of that one in the x direction. So I got 3 things. So I've got the 0.7 going up. I've got, for this, I've got minus 2 cosine 57 degrees, minus 2 cosine of the angle, plus the f. I get f is equal to 0.389 kips. All right, so what does that tell us? Well, when I draw my final free body diagram, it looks like this. What does that mean? Well, that means I have to have a friction force in that direction to keep this stable. Okay, in other words, even though there's a force going up that way, I'm not pushing the block upward. If we look back at this problem, in a way, there are 3 different things that can be occurring. One is that it's not going anywhere, it's not moving at all. 2, this force could push it up this ramp. Or 3, this force is not sufficient enough to keep it from sliding down. So I got this thing going, could go up, it could go down, or it could stay in place. When I look and I've found equilibrium, what do I need? Oh, this, in other words, this pushing upward like that, remember, the frictional force opposes the motion. It resists the motion, or resists the tendency for motion. So this pushing up that way means that the block wants to go down that way. So this wants to go down. So the block has a tendency to slide down the ramp. Now the question is, can I get that friction using the coefficient of frictions that we've been given? Well, mu static is 0.2, is given to be 0.2. That means our F max, again, that's the maximum friction that we can get, is 0.336. Well, guess what? Oops. 0.336 is less than 0.389. Remember, I take the 0.2 times the what? The 1.68. I don't take the 0.2 times 2 kips. It's always the n. So 0.2 times the 1.68, yeah, is 0.336, which is less than the 0.389 that I need for equilibrium. That means what? The block slides down because it's not in equilibrium. Because it's sliding down, we now go into mu k, and the mu k is 0.11, so it's 0.11 times 1.68 gives us 0.185. That's the actual frictional resistance that I'm getting, so I put that in there, and that is my final free body diagram. And again, what do I see? This free body diagram is not in equilibrium, and we use our F equals ma, sum of the forces equals ma, dynamics to analyze it. So, like I say, we're starting to create some free body diagrams that are not in equilibrium. And this is sort of leading you to your next class.